bekliyoruz ama manzara da fena değil. Ben pek tanıyamadım, yıllar geçti. Mustafa Akgül Hoca'yı tanıyanlar, hatırlayanlar var mı? Rahmetli, evet. Mustafa Hoca'yla, Akgül Hoca'yla aynı dönemde.
Beni duyabiliyor musunuz?
Buyurun hocam. So it's going to be, it will start at 2:30, unfortunately, the session.
Neden ses... Duyabiliyorsunuz da ben şey üretmiyor. Onun için önceden bağlanıp da yapmaya çalışıyordum. Bakayım şunu deneyeyim de yapayım onu.
Biz buradan host yetkisi verdik mi arkadaşlar? Verdik, tamam.
Başka türlü deneyeceğim.
Hocam,
Bir dakika bir
hocam,
slaytları background olarak almayı deneyeceğim.
Sayın hocam,
Biraz vakit alır ama
Şule Hoca bir fikir verdi şimdi. Slaytlarınızı bize hemen
belki
yollarsanız,
becerebiliriz.
slaytları yollarsanız biz buradan açalım. Şule Hoca'nın e-postasına yollarsanız...
Şimdi beni
gördük,
görebiliyor
geldi,
musunuz?
geldi. Buyurun hocam, görebiliyoruz.
Beni görebiliyor musunuz şimdi?
Görüyoruz, siz de görüyoruz. Slaytları da görüyoruz hocam. Siz bizi duyuyor musunuz hocam? Beni duyuyor musunuz hocam?
Geliyor mu? Beni görebiliyor musunuz şimdi? Ha, tamam. Onu soruyordum. Başka türlü şey yaptım da onun için. Okey. Tamam. Başlayabilir miyim şu anda?
Buyurun hocam.
Okay. Good afternoon, everyone. It's a privilege to be here to discuss a topic that sits at the quite interesting intersection of social science and computer science, which is the powerful synergy between social network analysis and graph analytics, which is what I'll talk about. My name is Konferansı, and I'm from the University of Waterloo. And over the next 45 minutes, I'll walk through this connection between the two fields. And the objective of this presentation is to build a gap and or bridge the gap, which shows that the two fields can benefit from each other. I originally prepared this talk to give at the ASONAM conference this year, which is really a conference of social network analysis people. And I made the argument there that there should be a better interconnection between these two. And about 10 days ago, I gave the presentation as a keynote at one of the VLDB workshops, which was only for graph analytics people, and I made the same argument there. So let's start with that introduction. So why am I arguing that social the connection. There should be a connection between social network analysis and graph analytics. Primarily because we live in an increasingly connected world. Social networks are everywhere, from our personal friendships on platforms such as Facebook and other social network platforms, and into complex collaboration networks in organizations. Even the intricate web of global supply chains represent the same thing. So understanding these networks is of paramount importance. Historically, we've approached this understanding from reasonably separate communities. One is social network analysis, or what I'll refer to as SNA. And these originate from really sociology and anthropology, and then the field made its way into computer science. There are lots of computer scientists who work in this area, but the origins are in social sciences. And the SNA really excels in interpreting social structures. They look at social structures and try to reason what is going on. For example, they try to understand why certain people are influential, or how groups form, how information gets disseminated in a network, and so on. So it's the strength of social network analysis is in meaning and context. But traditionally it has operated on small scale networks. The network sizes were not big. Now, of course, they've grown quite a bit. Graph analytics is based in computer science and mathematics, and really it focuses on scalable algorithms to process massive networks, billions of connections, millions of nodes or vertices. So that's basically what graph analytics does, and its algorithms are incredibly efficient in finding things, but the results can be some abstract, and so there needs to be an interpretation for it, which can be brought by social network analysis. And that's my core thesis in this talk, that these two fields are not only complementary but also mutually enriching. They can benefit from each other if they're properly connected. Sorry, I think I went. So let's start with talking about social network analysis a little bit. Social network analysis, or SNA, is the study of social relationships. That's what it is in its heart. And it uses the language of network theory. And individuals or entities that we model are represented as nodes, and the connections between them as edges, as I've shown here. There are key concepts like centrality, which quantifies the importance of a node. The concept of density, which is really a measure of how connected the group is, or the path length, which indicates how fast information might flow between these individuals or entities. So the defining characteristic of SNA is interpretation. It seeks to understand the meaning behind these network patterns. For example, SNA can say a person X is central to the advice network in a particular organization, and X may not have any formal role, but X may emerge as an informal leader. So it is really focused on these types of things. Just parenthetically, a little bit on the terminology. Social network analysis uses node and edge as the terminology, and I'll stick to that. But when I talk about graph analytics, I will choose vertex and edge, which I prefer because, as I will talk about later, many of these graph analytics platforms are parallel platforms, and there we use node to mean a computing node, and here I don't mean a computing node, so I'll make that distinction. The graph analytics is really focusing on efficient computation over very large graphs. As I said, its core is computer science and mathematics, and it looks at graphs merely as data structures of no. It doesn't matter where the graph comes from. It tries to do certain computations. Really, it handles very large networks. These days, we're talking about millions of vertices and billions of edges, and we find powerful algorithms to compute global properties of the patterns of the graphs and to find patterns there. For example, computing centrality for PageRank computation is one thing we all know, or detecting communities in massive graphs is another concern in this space. So the emphasis here is on scalability and generality. So, while a social network analyst might ask who is the most influential person in a 100-person company, 100 persons become nodes, and why is that person the most influential? Graph analytics might compute between a centrality that I'll talk about for all vertices in 100 million user network, efficiently telling us who would rank highest by that centrality measure, but it doesn't know how to interpret that in a social context. So that's really where the two fields diverge but touch each other. So let me say a little bit more about graph analytics. Social network analytics is reasonably well defined, but graph analytics is not that well defined. Mostly literature talks about graph analytics in using computation-based definition. So we're basically talking about workloads that access the entire graph. Every vertex in the graph is visited for the computation, and it really iteratively goes over the graph multiple times until a fixed point is reached or an end condition is reached. That's one definition, and that's the prevailing definition. So examples I've listed here are of that type. But we know from database field that there is also, when we talk about database analytics, we talk about OLAP type, online analytic processing type workloads. Data warehouses, slice and dice operations, and so on. There is an equivalent of those emerging in over graphs, as I've listed here. So there is, when we talk about graph analytics, we really need to be careful which definition of graph analytics we're adopting. And for this talk, I'm adopting the computation-based approach, just to be to put everything in context. So, with that introduction, what is the common ground? Graph theory is they both operate on the same primitives. We're talking about nodes or vertices and edges, paths in the network, and degrees. So these core structures define the relationships and the interactions across domains. And they also share metrics. We'll see that centrality measures, for example, are quite common in both SNA and GA. Community detection is common in SNA and GA. But they differ in how they look at these graphs. So there is a possibility for a unification using network science because they're really all there, they are both using networks and discoveries such as small world networks. You might have heard the 6 degrees of separation and scale-free properties. These works blend insights from both SNA and GA. So there's a powerful collaboration potential here. Graph analytics can perform operations on very large graphs, and then social network analysis can add to it the context of what is going on and why. So when we bridge these, we basically get quite a bit more. So that's why integration is crucial. In isolation, each approach has significant capabilities by significant shortcomings as well. SNA on its own, for example, would possibly be overwhelmed by the sheer size of today's networks. And conversely, graph analytics is powerful in crunching numbers, but it might churn out abstract clusters or metrics without providing the context that is needed. Algorithm in graph analytics might flag node 1, 2, 3, 4, 5 is central, but without context provided by SNA, you wouldn't know if that node is a celebrity, a bot, or a critical human connector. You wouldn't know. Then that comes from graph analytics. So the synergy here is clear. Graph analytics handles scale and complexity, and SNA in turn guides the analysis. So that's basically where we see where I see the connection. So my plan for today's talk is after this introduction, I want to give you some examples of some example applications where I will demonstrate this synergy, and then I'll talk a little bit about graph analytics platforms. How do these massive graphs get analyzed on our side of, and I'm a graph analysis person, and I'll talk about integration tools and methodologies, and then I'll end with a few comments on challenges and future directions. So I would normally in this talk give 5 examples, but we don't have as much time as I normally have. So I'm going to only touch upon 3 of them rather than 5, and I'll ignore the other 5, other 2. So let me talk about influence in networks. So we're basically talking about who matters in a network. In any network, certain individuals or entities play a disproportional role, and they have a disproportional impact. This influence can be manifested as being highly connected or strategically positioned to bridge different groups. And identifying these influencers is crucial across many domains. Marketing, you want to learn and target those individuals who can make your product go viral. In organizations, you need to find the informal leaders who really connect people and make things work. And in public health, you really want to identify these super spreaders, which are the influencers in that network, so you can have a control. So from SNA perspective, influence has long been studied, and they've been studied through a number of centrality measures that I'll briefly talk about. And the centrality quantifies a node's importance. That's why centrality is studied. The SNA also emphasizes the quantitative evaluation and understanding of a particular actor's role in this in a graph. So in graph analytics, the challenge is to do these efficiently on massive networks. So that's one side. The second side is that graph analytics has added the problem of influence maximization to this. So influence maximization is finding the optimal set of individuals to maximize information spread in a network. So integration angle here is clear. SNA provides the foundational concept of influence around centrality, and graph analytics provides the means to identify and leverage that influence at scale. So I won't go through these in detail, but I'll quickly highlight that social network analysis has identified a number of centrality measures. Degree centrality is easy. It just looks at the degree of each node, how many edges are connected to each node, and they basically look at the popularity of a node. Closeness centrality is a little bit more sophisticated. It actually says if a node resides on the shortest path distance to all the other nodes, it has a higher close centrality. So that this takes into account the fact that the nodes with higher closeness centrality are more efficient in spreading information and independent of other nodes. Then we have between the centrality that is used quite a bit. This quantifies how often a node acts as a bridge or intermediary on the shortest path between other pairs of nodes. So it is at the intersection of a bunch of shortest path. So these are actually our critical brokers who can control and facilitate the flow of information. And finally, there is eigenvector centrality, which is a node is important if it is connected to other important nodes. And of course, as I'm sure you know, this is the source of, this is how PageRank is computed. So when we look at graph analytics and how it takes these SNA concepts and operationalize them at scale, it provides a really efficient algorithms to compute these centralities on large graphs. The degree centrality is trivial to compute on even massive graphs for graph analytics algorithms. Closeness and betweenness are more computationally intensive, but we have developed advanced algorithms that and parallel computing to make it possible. And eigenvector centrality using PageRank is, as we know, highly scalable and computable on networks with billions of nodes. So this is, as I said, graph analytics adds to these the influence maximization, which is if I give you a budget of k nodes or k vertices, which k do you choose to maximize the influence spread? So which really k vertices on this graph allow you to spread information really fast? So graph analytics uses diffusion simulations and optimized algorithms for doing it, greedy algorithms with getting this. So this is really things like in viral marketing, picking the optimal seed individuals which you target in your marketing campaign. So you can see an application for this might be a corporate communication network which captures email communication. Vertices are employees, edges are frequent emails, and graph analytics would compute these degree and betweenness centrality measures very, very quickly, or and run influence maximization, and SNA can then bring interpretation to this, telling you what it might mean. And you might find hidden bridges. For example, an engineer that is not a manager, doesn't have a formal role, but has the highest may have the highest betweenness centrality, saying he's critical. The engineer is critical for connecting two departments, and so on. So that's the type of thing that you do. So I went too fast. So the next algorithm that I'm going to look at is link prediction, which is really very common, of course, in our systems that we use. We're now shifting focus from understanding existing networks to anticipating their evolution. That's what link prediction does, and that involves inferring which pairs of nodes that are not currently connected might be connected in the future. So the importance of link prediction is vast. It's the engine behind people you may know networks that we all know. From an SNA perspective, we understand why links form. So if the link is going to form between two nodes, we can actually tell why they are forming. So theories like homophily suggest that people connect with those who are similar. So we connect to people who are similar to us. Triadic closure says that if A is connected to B and A is connected to C, it's likely that B will be connected to C. And opportunity and propinquity highlights that physical or organizational proximity increases the chances of connection. The graph analytics perspective here is that it takes social principles and quantifies them. It measures the similarity between nodes, counts common neighbors, uses machine learning algorithms to combine multiple factors in predictive machine learning, and then predicts the future. So you can scan millions of potential pairs and rank the most likely connections that are going to form. So the Libin, Novel, and Kleinberg work is probably the classical in this area. So the heuristics for link prediction are many, and they start with intuitive heuristics. So common neighbors is the straightforward one. Basically, this heuristic says it just counts how many friends two people have in common, and the higher the number is, the more likely that they will connect with each other. Jaccard coefficient or Jaccard measure is a bit more careful. It looks at the proportion of shared neighbors to all the neighbors, and then says if that ratio is high, then the two nodes are likely to connect. Others score defines common neighbors by saying if I'm connected to a rare shared friend, they're more important and therefore that should count more towards my score. And the preferential attachment suggests that the likelihood of forming a link is proportional to the product of the node's degrees. So it looks at the degrees of each node and takes the product, and the higher it is, the more the two nodes are likely to be connected. So these heuristics are computationally efficient and often serve as strong baselines for more advanced methods. So the more advanced methods they use machine learning So, the modern graph analytics goes beyond simple heuristics that I talked about. And one approach is feature-based machine learning. Here we assemble a rich set of feature vectors, and each vector is for one node. And then we use heuristics like common neighbors and attribute similarity. So the vector captures a lot of things about the node and the positioning of the node in the network. We then train a classifier on historical data using these vectors, and the model learns the optimal combination of these features, and then uses this to to predict. And it can capture complex nonlinear relationships that the single heuristics might miss. The next modern approach is graph embeddings, which is more advanced. It generates a low-dimensional vector representation for each node. Node to vec and deep walk are examples. So it captures the network content, and the nodes with similar neighborhood patterns end up with close vectors. So if two nodes are close in the vector space, they are also very close in the actual space. So they are likely to be connected. So that's the link prediction that you do. And finally, of course, there is the graph neural networks, which are now the state of the art. And these are deep learning models that learn from network representation and predict links by iteratively aggregating information from a node's neighbors. And they can learn incredibly complex higher order patterns and effectively integrate both network structure and node attributes. So over the property, what we call the property graphs. Okay, so those are the techniques that we use, and these are very, very fast on the graph analytics side. And of course, the example here is very straightforward. All of the social networks have this recommendation systems on whom you should connect, and those algorithms are exactly this link prediction algorithms. They're predicting that there should be a link between you and somebody else, or there's a high likelihood that there will be a link to you and somebody else, and suggest you that connect with them. So the other final application that I'm going to look at to demonstrate this connection between SNA and GA is finding roles in the network. So this is going beyond communities. So communities group the nodes by their dense interconnection. So interconnection within a community is denser than the interconnection across communities. But here the roles categorize the nodes in the network by the patterns of connections they have. So it is possible that you might have two nodes in two different communities with the same role, but they're not connected. So in the example that I show you, the hub nodes are not really directly connected, for example, but there are brokers which really connect different nodes. So it is really the roles that we want to connect. And why we want to do this? A number of reasons. One is simplification. Instead of analyzing millions of nodes or individuals that the nodes represent, we might be able to just analyze a handful of roles and to get the answer to what we're looking for. And it can also allow for transfer of insight. So if we know a node's role, we can sometimes predict its behavior by analogy to the other nodes that have the same role. It also aids in anomaly detection in the network, and it can provide quite a deep social insight into the functional division of labor in the graph. So the way that these are formalized or conceptualized in SNA are through the idea of equivalence. So the strictest form of equivalence is structural equivalence, where two nodes have exactly the same neighbors. So A and B in this graph have exactly the same neighbors, so they're structurally very similar. That means that they are perfectly substitutable in terms of their network position. Okay, I mean this is powerful, but it is a very strict condition that is rarely met in practice. So the other equivalence that might be used is regular equivalence. Here, the nodes are nearly regularly equivalent if they connect to others in the same roles. So they are not really connected to the same neighbors, but they're connected to the others in the same roles. Not exactly the same individuals. For example, all managers in a company are regularly equivalent because each connects to all the employees in that company. So it connects to employees and possibly a director. So the specific employees and director for each manager might be different, but that doesn't matter. Block modeling is an SNA technique to detect these equivalence classes, because that's what we're looking at. We're trying to find equivalence classes, and the output is of these block modeling models is a matrix that shows the high-level interconnected patterns between role groups and abstracts out the individuals. So the SNA interpretation then gives meaning to these roles. For example, a block model might reveal a manager role that consistently sends emails to an employee role block and receives from an executive role blocks. And the SNA can provide interpretation that will help us understand the division of labor in this organization. Where GA helps in role discovery is to provide certain algorithms that do these very fast. One approach is feature extraction combined with clustering. Here we compute a set of structural features for each node or vertex, such as its degree, its density of its immediate neighborhood, and so on. And these features create a digital signature or structural signature for each node. And algorithms such as ROIX and use advanced matrix factorization techniques to infer what the rules are in this matrix. And then we use clustering algorithms to group nodes with similar feature vectors, and that gives you quite a bit of information. Another approach is matrix factorization, and matrix factorization of the adjacency matrix itself, and this involves decomposing network structure to uncover latent role patterns that often result from models that assign probabilistic roles and define how those are impacted. And finally, oops, sorry, I went too far. Graph embeddings can also be used for role discovery by generating how low-dimensional vector representations that specifically capture structural similarity. We can then cluster these embeddings to identify role groups. And this allows us to find roles even if the nodes are different and in different disconnected parts of the graph. So it's clicking too fast. So an example of the use of this can be again an email network, but in this case, you might remember from early 2000s the Enron scandal in the US. So the Enron email network analysis, where the nodes are employees and edges represent significant email communication, and a role mining algorithm was applied to this data set, and it was able to quickly determine the structures, the executives, the managers, the staff, and so on. And more importantly, the algorithm also discovered a distinct emerging liaison role, and these were small set of individuals who were in different formal departments, but they showed consistently a consistent pattern of cross-departmental connections, and this was helpful. So I think the whole analysis reduced the complexity from a very large number of nodes to a very small number of nodes. So to summarize this section, the tasks that I discussed have different but complementary foci when we look at it from SNA perspective and when we look at them from graph analytics perspective. Okay, so the next thing I want to talk about very briefly is what platforms have we developed to do these graph analytics over these massive networks and graphs when social network analysis struggles with smaller graphs. And I will be fast here. So the first thing you might think if you're coming from a computer science background is, well, first of all, you notice that almost all of these systems are scale out, so they're parallelized. So that's how we gain what part of that's part of the important issue in being able to scale up this well. And if you notice that they're all scale out, then you can actually say, well, we had developed all these techniques using MapReduce and Spark, and so those systems, can we not use them for graph analytics? The answer is yes, but that's not a good idea because those systems do not really perform well on iterative tasks. I don't have time to get into it, but it has been discussed in literature quite a bit. So we have developed specialized platforms and some of these platforms have morphed and the ideas have been incorporated into the modern graph DBMSs. So the best way to focus on this is to highlight that we can look at all the systems that have been developed for graph analytics in the two-dimensional space. So on the x-axis, we have the programming model, how these systems allow you to program. On the y-axis are the computational model. I will go very fast over these because we don't have time to get into them in detail. On the x-axis, the programming model, basically the alternatives are vertex-centric, partition-centric, and edge-centric. Vertex-centric, you might have heard of, is basically says when you're programming the analysis task in these systems, just concentrate on what each vertex needs to do. So each vertex gets some messages as state information from its neighbors. It does a computation, and then it sends its own state to its neighbors. So the really important thing here is you focus on writing what the compute function is going to be. That's it. The rest of it, the platform will take care of. So if we write, if we can figure out what each vertex is supposed to compute, then we can compute these all of these vertices or many of these vertices in parallel in a scalar system and do it very fast. So that's vertex-centric. So there is a compute function on each vertex. Partition-centric basically says this is fine, but there might be too much communication between vertices. So why don't we find the connected communities. And within each connected community, we run a serial algorithm. But when we're going across communities, then we do exactly what vertex-centric does, which is that we take the state of the entire subgraph, send it to all of our neighboring subgraphs, and then each of those neighboring subgraphs take this state, do their computation internally, and then share it again. So that's partition-centric, which basically goes from thinking like a vertex to thinking like a partition. And then there are eccentric programming models, which basically they are the dual of vertex-centric, which says that instead of thinking of each vertex, think of each edge and write what the computation is going to be on each edge. So that's on the programming model. On the computational model, the most popular and well-known algorithm is block synchronous parallel, which is Valiant's algorithm from quite a number of years ago. And Valiant's algorithm is not designed for graphs, but can be used for graphs. And the block synchronous parallel, or BSP, works in the following way. You have a number of parallel computing nodes. These are computing nodes, not vertexes in the graph. The computing nodes do their computation, and then once they finish their computation, there's a synchronization barrier where they exchange information among themselves. So everybody gets everybody else's the computation results. And then a second iteration starts. And the second iteration, they take these new inputs, do another computation, and then synchronize again and go. So do you have these synchronization steps? And you go one iteration, synchronize, another iteration of computation, synchronize, and you continue like this until the fixed point is reached, which is that none of the vertices see any change in their state. When they recompute, the state is the same as the past state. So that means that they're not going to change anymore. It's time to stop. Or this can take a long time. So in things like PageRank for when it's computed using BSP, you typically give a certain number, run 100 iterations and then stop. So that's one approach. The other approach, of course, is asynchronous. So you remove these synchronization barriers. You basically tell the computing nodes, when you compute your state, don't wait for synchronization barrier. Just share the state among yourselves. So this actually speeds things up, and the computing nodes can use up-to-date state, but it also requires locking because you have read-write conflicts, and that locking has high overhead. And the gather, apply, scatter is a third computation mode where which is really very similar to BSP, except that in BSP, when computing nodes compute their states, when they push their state to their neighbors. In the gather, apply, scatter, the neighbors pull. When they need them to learn the new state, they pull and go from there. So that's basically what. There's a whole bunch of platforms designed here, and most of the work is vertex-centric, block synchronous parallel, but there is some on the other along the axes of the others. But there is nothing there because it's hard to develop those platforms in that space. All right. So I think the more important thing is that these platforms were in the 2000s, but now people are trying to push these and understand what graph analytics connection to machine learning is, and they're really because these problems go beyond the simple platforms, and they find 4 analytics paths here. So you basically do vertex analysis, which outputs a state for each vertex, and then you can use vertex analysis plus machine learning, where the analytics stage outputs vertex embeddings for downstream machine learning tasks, or structure analysis, which outputs subgraph structures, and structure analysis and ML. And this was in a tutorial at the KDD conference. And the interesting thing in that paper is that they look at all of the existing tools to actually indicate where they fit and what functions they provide. All right, let me very quickly synthesize and add, because I've started late, but I'm running out of time in any case. So the integrating principle here is that the problems that we looked at, or the tasks that we analyzed, demonstrate that there is an undeniable value of combining social network analysis with graph analytics, and that gives you a holistic network understanding. We can do this across all of those tasks that I talked about, and these topics are not isolated either. The tasks that we talked about, they are interconnected. When you know both the key people and the community structure, for example, in a network, it will allow you to identify influences within each group as well as across the network. And understanding communities will also let us understand how diffusion might work and so on. So the integration is the need for integration is real. And the good news is that this is now starting to be, or increasingly being, facilitated by unified data and platforms for analytics, and they allow seamless analysis across these dimensions. And then the idea is that you can then get to some actionable insights here. So what are the tools and platforms? For example, we have graph databases and query engines, the examples I've given here for data storage. We have flexible analysis and rapid prototyping tools such as NetworkX libraries, and Python and R are in this space as well. They offer a wide array of SNA measures and so on. And at the cutting edge, we have graph machine learning frameworks like PyTorch and Geometric, and then finally visualization and interactive tools like Gephi and so on. So together, these tools embody the integration, allowing practitioners to store, compute, and learn from, and also visualize data effectively. So there are systems starting to emerge that will enable this integration that I talked about. So let me end with key challenges and look at the future. Of course, one of the biggest challenge is data quality and completeness of the data that we have. These are persistent issues in any time we deal with data, unfortunately. Real world data is often messy, and they have missing links, outdated attributes, or noisy connections, and this incomplete and messy data can significantly bias our analysis. So that's a problem. The second is privacy and ethics. When you're dealing with these social networks and looking at the properties of these social networks and analyzing them the way that we discussed, this can inadvertently reveal highly private information. And there are serious ethical considerations regarding the use of these. And there are regulations as well. European Union's GDPR is one example. And they need to be integrated. Well, the tools need to be compliant with all of these. And then, of course, scalability and complexity remain ongoing battles. While graph analytics provides you with these tools, truly massive networks with billions of nodes still push computational and memory limits. So these are really not going away anytime soon. There are also intangible challenges, which are more social challenges, which is that because we're talking about interdisciplinary communication between different groups, the language gap between us could be serious. We use different jargon. For example, social networks and network analysts use closure, and graph analytics people use clustering coefficient, and the miscommunication is possible, and that can bias it. The interpretability of these models is a significant issue, especially when you move to predictive ML models. These are operate right now as almost black boxes. There is movement towards explainable AI, and that's really important because in many of these tasks, it's not sufficient that you tell me what is going on. You need to be able to tell me why you reached that conclusion. Consider healthcare networks where you cannot just rely on what the analysis tells you, but you need to know the why. And then of course you have multiple shareholders, and convincing them is difficult. So looking ahead, we're really looking for. I'm hoping for a integrated network analysis, and that would be incredibly exciting, and that will focus on making the approaches smarter and fairer, hopefully, in that stuff. And as I said, I do expect significant advancements in explainable AI and more transparent graph learning techniques. We need to keep pushing for bias and mitigation and fairness. That's important. There is going to be improvements in dynamic and real-time analysis. This is really important. None of these networks or graphs are static. They change. As they change, we need to be able to adapt. And then, and hopefully, there will be deeper integration with other fields in AI, such as computer vision, natural language processing, and so on. So there is all of those. So let me end by thanking the upper row are my current and past students and postdocs who worked on graph analytics with me. The second row are all my colleagues from the various universities worldwide who have been working, with whom I have been working. And then I also acknowledge that I've used Gen AI tools in both structuring this presentation and also generating some of the infographics. So the concluding remark is that I can restate my thesis that the synergy between social network analysis and graph analytics provides an unparalleled opportunity for understanding and shaping network systems. And there are ways of achieving this that we need to take advantage of. And this collaboration is not easy because it involves different communities, but it will lead to powerful understanding of these networks. With that, thank you very much. I think I'm a bit late, but I started late, so I hope I will be forgiven.
Hocam teşekkür ederiz.
Okay.
Sesim geliyor mu size?
Stop sharing?
Yes, please. You can stop sharing. Benim sesim size geliyor mu?
Duyuyorum, zor anlaşılıyor ama duyuyorum.
Duyuyorsunuz. Hocam burada makine öğrenmesi çalışan oldukça büyük bir grup var. Bu sizin sunumunuzdan, bu değerli sunumunuzdan yararlanacaklardır herhalde. Çalışmalarını makine öğrenmesi ve derin öğrenmeye götürmek üzere. Vaktimizden dolayı bir soru alacağız. Hami hocamız size bir soru sormak ister.
Tabii.
Professor Tamer, thank you very much for your presentation. This is Professor Hami from Gelişim University. What I understood is what Cambridge Analytics did. You remember Cambridge Analytics? So all those nodes, entities, you say they are individuals. And what we are trying to do is try to learn their political views if they are going to vote for X party or that party. And we are trying to pinpoint those who are in between. They haven't decided. And we want to pop up the good news about our party. Can we use this social network analysis so that those 10-20% who haven't decided which party to vote, so then they can vote for our party? How can we interfere elections in any country by manipulating these people? It's a little bit social psychology. Thank you.
Okay. I'll answer. Some of the background, the sound was coming and going, so I think I understand the question in the general context. The details I missed, but I think the fundamental issue that you need that I would suggest you focus on is the question of what it is that you're trying to analyze. I think that's where the question comes. I selected for this talk 3 tasks that for analysis of the network, and the question that you might want to focus on is what is it that we want to learn. That's number 1. Number 2, social network analysis and graph analytics techniques can definitely be used if your underlying representation is a graph. So if you can map what you have into nodes of a network, and if there are interconnections between these entities, and you can represent them as edges, if that representation makes sense, then you have the groundwork for network analysis. In this case, we focused on social networks, but network analysis is network analysis. You can do the same thing. The interpretation will be different. So you can always do that. So the first thing is whether a graph representation is the best thing for the system you're considering. The second thing to look at is that if it is, then what is the task? What is the analysis question that you're asking? And then one of these methodologies might actually be of help.
Sayın Hocam, teşekkür ederim. Ben de bir Waterloo mezunu olarak sizlere merhaba demek istiyorum. Arkadaşlara burada bahsettim.
I think my time is
Profesör
up, and
Bruce Simpson benim doktora hocamdı. Rahmetli oldu geçen sene, 2 sene önce. 74-79 arasında ben de Waterloo'daydım. Sizleri burada dinlemekten büyük onur duyduk. UBMK konferansı size bir plaket hazırladı. Onu sizin adınıza ben alıyorum. Şule Hoca'ya teslim edeceğim. O da size bir şekilde ulaştıracaktır. Katkınızdan dolayı çok teşekkür ediyoruz. Kanada'ya selamlar.
Ben çok teşekkür ederim. Sağ olun. İyi başarılı toplantılar. İyi günler.
Çok sağ olun. Teşekkür ediyoruz. Oturum